The functions we've been working with have been algebraic. That is functions that look like this. I'm going to use y here. So y equals something like this. We might have had x to the b. Here's an example, right? Y equals x to the third, where the form is this. What we have is, on this side, what you have is a variable raised to a constant. And these are called algebraic functions. What we're going to do now is switch the variable and the constant, and we're now going to write this. Y equals b to the x, sort of like something like maybe y equals, now just switch these. Instead of x to the third, we would have 3 to the x. And this side over here looks like this. Now you have a constant raised to a variable. So this is the first time that we're going to see something where the variable appears in an exponent. And these functions are called exponential. So I'll make a little bit more careful definition here. What we'll have is this. F of x equals b to the x, but we have to put some conditions on b. b, the base, can't just be any number here. Here's what we require. B has to be greater than 0, so it has to be positive. Be careful here. It's not an equal to here, so b cannot be 0, it can't be negative. This base has to be a positive number, like the 3, but it can't just be any positive number. What you have to do is we have to take one number out, and that's the number 1. I'm going to refer to this function right here with those restrictions as the basic exponential function. We're going to generalize it really soon. Let's look at some properties of this function here. Now what I'm going to do is I'm going to start out by drawing a number line of the base numbers here. So I'll draw a number line, maybe. There we go. All right, I'll label it B because that's what I'm going to put my B values as. Now the B, of course, is the base. So this number is where I'm putting the base. Now the base has to be greater than 0, not equal to 1. So let's just put a 0 someplace. Now I'll put it, okay, that's not the 0. That's just a hole in the graph here. I'll put that's not 0. That's 0, right? That'll be our 0. And what we're looking at now are just points out here except 1. So I'll put an open circle at 1 here also. I'm just going to tell you what happens here and show it to you in a little while. But if you pick a base in here, like a fraction between 0 and 1, like a half, a third, 5/6, something like that. Let's do that. If you pick a value in here, what you get when you graph this function is this. Just to get a quick little sketch here. Here's the x and the y-axis. The curve is going to come down and look like this, and it's going to approach the x-axis. The farther out we go, the closer to the x-axis it gets. It will never reach the x-axis, but it'll get closer and closer. That's our origin right here. And this point right here, right, well, you know what that is. Because if you let x equal 0, right here, if x equals 0, what do you get here? B to the 0? And we're saying b is not 0, so the non-zero number to the 0 power is 1. So this basic function crosses at 1 and has this descending shape. There's a name for this function here. Well, it's an exponential function, but more explicitly, it's called an exponential decay function. And you might think of it like this. If this is time, now if it's time, we wouldn't have anything over here. We don't have negative time, so the curve would start here and go down like this. So if this was time, as time goes on, what happens to the amount of something that you have? You start off with this amount, and then it just decays over time. Might it get smaller and smaller? This might be something like you take an aspirin or some drug at time 0. So if this is time, at time 0, right, you start with that amount of the drug in your bloodstream, and then just what happens as time goes by, right? As time goes by, well, your body metabolizes that drug out, it breaks down, and eventually it goes to 0. Not in this model, because it never actually touches the x-axis, but you can see what's happening. That drug is decaying. So we call it the exponential decay function. Now, what if you choose a value out here? If you choose a value out here, then you get a graph that looks like this. Kind of a reflection in a sense of the one that we just drew, that decay function. It starts off like this, cuts through the y-axis, and increases like this. So over here, I'm back to the left again. This is the graph of b to the x, where b is a fraction between 0 and 1. This over here is b to the x, where b is some value greater than 1. Like this might be 1/3 to the x. Here's an example. I'll write it down here. Probably should have done that before. Here's an example. F of x, pick a fraction. 1/3 to the x. This one over here, this might be f of x equals 3 to the x. So what you get is this increasing behavior, and this one here is what we're going to have is, again, when x is 0, b to the 0 is 1. So this curve crosses here at 1. That basic function crosses at 1. And this function here is called an exponential growth function. An example might be at time. If this is time, then again you would not have anything over here because that would be negative time. But if this was time and you had, say, a dish of bacteria, as time goes by, what happens to that bacteria? It grows, and it grows, in this sense, exponentially. So this is called an exponential growth function. So these are two common functions that occur in a lot of real-world applications. So you'll want to know these. Put them in your library of functions in your head. So when you see a curve that looks like this, you might think of something b to the x, exponential decay, where the b maybe is a number between 0 and 1. And when you see a curve look like this, you might think, oh, that's exponential growth, where b would be a number bigger than 1. I've just redrawn our b number line and the two curves that you get when you choose a number between 0 and 1 and a number bigger than 1. So this one here, right, that's the decay curve. So if you choose a number for the base that's between 0 and 1, you get this decay curve. If you choose a number over here, bigger than 1, then you get the growth curve. Not too long ago, I told you I would tell you what happens if b is equal to 0. That's this case right here. Right? So b has to be positive, but it cannot be 0, or it can't be 1. So let's take a look at each of those cases. Here's why it can't be 0. Let's look at that. If b is equal to 0, then here's what the function looks like. It looks like f of x equals 0 to the x, but 0 to any power is just 0. So really, what we're looking at here is this. Could you graph this? Y equals 0. We know what this looks like? This turns out to be, all right, let's draw our axis here, x and y. All right, y equals 0. This is just a straight horizontal line passing through 0 on the y-axis. Right, I'll do this one just so you can remember. What if you had y equals 3? Wouldn't that just be a line that passed through 3 on the y-axis, just that horizontal line? If it was -5, that line would be down here. But we've got y equals 0, so it's just a line that passes through 0 on the y-axis. And surely when you look at this curve, I mean, it's just flat, right? It does not look like this or like this. It does not have that decreasing decay behavior or this increasing growth behavior. This is just flat. So because it does not have this decay or growth feature, we just rule that out, right? So no b equals 0. Now what happens if b is equal to 1? Well, then you get this function. F of x equals 1 to the x, but 1 to any power is 1. So now we're just looking at this. F of x equals 1. Let me actually draw that 1 so it looks like a 1. So f of x equals 1. Now, you know how, I'll just make it y so it looks more familiar. So this would graph just like this. Here's x and y, right? This, our origin. This is a horizontal line that passes through 1, right? That passes through 1. So this curve here, that curve does not have this decay feature or this growth feature. So again, we're going to exclude it, right? So what we're going to say is we don't want b to be 0 and we don't want b to be 1. But there is another case. What happens if the base is less than 0? All right, we've excluded 1, we've excluded 0. Why are we excluding these numbers here? What happens if the base is less than 0? Let's suppose we have this function. Say b is equal to -2. All right, then our function would look like this. F of x equals -2 to the x. Let's make up a table. All right, so if x is 0, what do we get here? -2 to the 0, which is 1. Okay, let's make a little graph actually here. We can do that right down here. So if we start at 0, we are at 1, which is reasonable. That looks like our other graphs. But what happens now if x is 1? If x is 1, we get -2 to the 1, which is -2. So if we go out here to x equals 1, where are we? We're down at -2, so I'll plot that point. All right, now already we're down in negative territory, and if you look at these graphs here, they're always above the x-axis, right? All the output is above the x-axis. All the output's positive. Now at 1 unit, we're already negative, so already it doesn't look like one of those curves. What if you put in 2? If you put in 2, if I can do it, you put in 2, you get -2 to the 2. -2 squared is 4. So if we go out here to 2, we're up at 4. And then if we go out to 3, we get -2 cubed is 8. Well, it's actually what? It's actually -8. So if I'm out at 3, okay, I go out 1, 2, 3, I'm down at -8, so I'm way down there now. All right, so now it looks like this is what's happening. It looks like the curve's going to look like this. Now, it doesn't look like this, so I'm going to erase this after I draw it. But doesn't it look to you like it's going like this? Just alternating back and forth here. It looks like that. But that's not what's happening. Now, that behavior, sure enough, that behavior right here does not look like any of these behaviors. So that's one reason we exclude it. But let me erase that now. If I put in 1/2, I will get -2 to the 1/2, which I could write as the square root of -2. And as you know, that is imaginary. Now this axis here, these are real number lines, right? That x-axis, this is for real numbers, this is real numbers. So if I come out here to 1/2, I get an imaginary number. That means there's nothing here on the graph at all. It's like a hole. Now I'm going to draw that curve back in here again. We'll see what's happening. So we thought it might have looked like this, right? We thought it went like this. But now we see that at some points it doesn't even exist. So if I come out to 1/2 and follow it down, there's a blank. There's a blank there. So if I try to draw a blank in that spot, it's a little difficult to do. What do I get here? If I try to erase that little spot right there, I can't do it. Anyway, what's going to happen here is this. Right at that point, I'll draw it here. Right at that point, as the curve is coming down like this, there's going to be a hole right there. And not only there, but there is going to be a hole at every even fraction, like 1/4, 1/6, 1/8. So here's a curve that we thought might be continuous with this kind of up and down behavior, but what is it really? It's really full of holes. Very interesting graph. So there is the reasons why we exclude negative numbers, 0 and 1.